and start today with a warm-up. You've been working a lot with polynomials and graphing them, and then you learned how to write equations of them. Please pause the video and go ahead and write or sketch the graph of this without using your calculator, and then also list the 4 graphing characteristics I listed off to the side. So what degree is this polynomial? 8th degree. There's 1 here, there's 3 here, and there's 4 here. So if I multiply all those together, I get x to the 8th power. I get 2x to the 8th power. So therefore, if you remember when we talked about it, when the degree is even, it looks something like this or something like this. Versus when it's odd, it goes in opposite directions. So it should give you an idea as you're going through and graphing it to make sure that you have the correct degree along with your graph matching up. Okay, so I know at +1 it's a cubic shape, so that either will look like, like this, or it'll look like this. This is a 4th degree, so at 3 it's going to flatten a little bit more than if it were just a parabola. And then this goes through like a line, so that's going to go through like a straight line, either like that or like that. So looking at my orientation, I can see that it has a positive orientation. Otherwise, I could use the y-intercept to possibly help as well. But because the y-intercept happens to also be an x-intercept, that's not super helpful for when we're looking at what's going through. Okay, so positive orientation, all of these start with x's in the front, and that is positive. Therefore, from 1, it's going to go up and to the right. However, at 1, it's that cubic shape, so it's going to look like this. Therefore, flat coming through. So we can see kind of there's that jog in there. Comes down somewhere or another and then comes back up. And then at -3, it flattens and bounces back up. Okay, that may be flat a little too long. Let's make that a little better. There we go. So, looks kind of oddly shaped, but that is our 8th degree polynomial. So, graphing characteristics as well, real quickly. We also know we have x-intercepts at -3, 0, and we also have an x-intercept at 1, 0. So we have 3 different x-intercepts. There are repeated roots, though, that are in there. Domain, all real numbers. I left out range because I don't know how low it goes. I'm just putting it right there. I don't really know at what point that gets down to. Now, when you get into calculus, you're going to learn what those low points and high points are along the way, but at this point, we don't know any. And then the last thing is our end behavior. Because this is an even function, our ends are going to be the same. So as x approaches infinity, y approaches infinity. And as x approaches -infinity, y approaches infinity as well. Remember, you always start with your x values. So if it was an odd degree, then they would go in opposite directions. So we're going to work on learning a new type of number, which are called imaginary numbers. And imaginary numbers are going to help us when our graphs don't cross our x-axis. Because remember when we talked about roots and we defined roots? Roots are the value of x when y is 0. And we looked at graphing when we had real roots. But we're going to get non-real roots, which are called imaginary. So we're going to learn how to find imaginary numbers in today's lesson. So to begin with, I gave you a quadratic, x squared equals 2. So how do you undo a square? You square root it, right? So when you solve that, how many solutions are you going to get? This is that tough thing. Remember, if I give you x squared equals 4, I'm just going to make these nice numbers. What squared gives you 4? 2 does, as does -2. So therefore, there are going to be 2 solutions when you solve that quadratic. There are 2. How many x-intercepts would it have? Think about the graph. If I sketch the graph, it's a quadratic shifted down 2 units. So how many x-intercepts are there? There's 2 as well. So would you please go ahead and finish solving that and write your actual answers out? So x equals positive and negative square root of 2. And we can decimal approximate those. It's approximately positive and negative 1.414. Okay, so radical approximation. A lot of times when we solve problems, we are going to find the exact value, unless I need to use that value to then go and graph something. So whenever we solve, we always give an exact value. Please remember that, because we're going to be doing that quite a bit. So simplified radical form, and we're going to practice that in this chapter. Hopefully you did that in your homework problems and didn't just copy down the work, because we're trying to get you ready for that now that you're doing 821, because we're going to have to simplify, because our calculator can't do it for us. So what we learned, though, here was this square root number. So maybe you learned that in 7th grade, 6th grade, about irrational numbers. So you can go ahead and pause this and read through the whole thing. But when push comes to shove, what it came out to is how do we solve a problem that isn't a perfect square and I'm trying to square root it. So they had to incorporate these numbers called irrational numbers. So more different types of number sets were introduced when we needed them. So when we were solving quadratics like this one, and we didn't know how to represent the square root of 2, we had to bring in what were called irrational numbers. Up until then, we learned all about rational numbers. The similar thing is going to happen now. We are going to have to learn how to solve imaginary numbers. So this problem is helping us with that. So mathematicians resisted the ideas that some equations were not solvable. Because you knew that x squared plus 1 equaled 0, but it can't be solved. Because if you graphed, instead of the 0, if you put y in there, y equals x squared plus 1, sketching that, shifting up 1 unit, there are no x-intercepts. So if we replace 0 and y, there's no x-intercepts. So how do we have solutions to it? Well, we can still solve it. So and this is where imaginary numbers came through. So really quickly, when you're trying to solve this problem, you end up getting x squared equals negative 1. Well, the problem is what number squared makes negative 1? No number squared gives you a negative 1. When you square a number, it's not going to become negative. It's positive, no matter what, whether you put in a positive number or a negative number, whether I put in a fraction or an integer. It's impossible to do. So they had to figure out how do we actually make this work, because we're not able to take the square root of a negative number and get a real number. Listen to that carefully. I can't take the square root of a negative number and get a real number. I get a complex number or an imaginary number. So when your teachers before told you, hey, you can't square root a negative, I always want to add on the caveat and get a real number, because you can square root a negative number. You absolutely can. It's just not real. So what ended up happening is Bombelli, he's this gentleman from 500 years ago, used a formula to find the roots of a third-degree polynomial. So we know how to find the roots of a quadratic. We can do the quadratic formula. We can factor it if it's factorable. But we don't have any kind of formula like that for a third-degree polynomial. So therefore, he came up with some formula, and what ended up happening is the square root, the number underneath the square root became a negative. So instead of giving up, he just treated it like, hey, we're just going to go with it and be okay with it. And the incredible thing that happened is eventually that imaginary number disappeared from the solution. And more specifically, it worked. You ended up getting a real number for the solution. So this is what's called imaginary numbers. So we're going to work on the imaginary number. So in the 1500s, the Italian mathematician invented the imaginary number, the square root of negative 1, which is now called I. So I, by definition, is the square root of negative 1. And this was the part that was the issue, right? The square root of negative 1. So he defined the square root of negative 1 just as I. So then what you can do is you can square both sides. So I can square both sides of that equation, which gives me I squared equals negative 1. And those two pieces is what we're going to use when we go through and we simplify, especially with square roots. Remembering that I, by definition, is the square root of negative 1, and I squared is negative 1. A quick note for you, I sometimes can look like a 1. So you'll always see me curl my eyes. And that's just more so that you know it's not a 1. So as we go through, we can rewrite the square root of negative 16. And this is how we're going to be able to undo those issues. So the square root of negative 16, that negative is like a negative 1. So it's 16 times negative 1. It's the square root of all of that. Okay. However, the really great thing is we just learned negative 1 is exactly the same thing as I squared. So instead of negative 1, I can represent that as I squared. So I just substituted what negative 1 was, and it's I squared. And now, when I have square roots, I can square root over multiplication. I can't square root over addition and subtraction. That's like setting an exponent across addition and subtraction. You cannot do that. But you can send an exponent over multiplication. That's like this property. That's a to the x, b to the x. So therefore, I can square root the 16 and I get 4, and I can square root the I and I get 4i. So the square root of negative 16 is equivalent, exactly the same thing, as 4i. So what you're going to do is you are going to use the definition of I to simplify out these 4 problems. Now there's typical math in there as well, so go through and do the regular math. But also use this idea that square root of negative 1 is I, and I squared equals negative 1. Your I should not have any exponents on it, otherwise it's not simplified. So pause and do this. So the first one is status quo, just like the square root of negative 16. The second one's a little different. It's all multiplication. Keep in mind that. So there's a multiplication sign between the 2 and the I here and here. So it's just multiplication. So I just reordered them. And I got 6. And then I times I is just I squared. And I squared, we know, is negative 1. Therefore, this is negative 6. Next 2. This last one is exactly the same as the last one, the one above was. So just simplifying this out, this is 5i. And then this last one here, C, I squared the 2i. So I wrote 2i times 2i. Remember, you're squaring outside the parentheses. So you have to square each of those pieces. And then what I did is I combined 2 of the i's together. Instead of doing all 3 of them, I just combined 2 of them together. Because we know by definition, since I is the square root of negative 1, I squared, therefore, is negative 1. So then I can rewrite this like that, and then still multiply it by I. So now I have that negative times negative 20, so that's 20, and then times I. Okay, so that's just practicing I, just being able to simplify them out. Because what's going to happen is you're going to get equations, and you're going to be solving things, and you're going to get these imaginary types of numbers in here that you have to simplify. So in this problem, we would have to take a look at, does it cross the x-axis? So I graphed this already for you, so it's here. And here is the x-axis. I'm not sure if you can see that or not. So there's my x-axis. So does it cross the x-axis? No. Therefore, if instead of having a y, if it was a 0, does that have any real solutions? No, absolutely not. Since I put 0 in for y, that should be able to figure out where it crosses the x-axis. So therefore, there would be no solutions for it. But this is the type of question that you're going to be working on. They're going to be equations set equal to 0, not functions that you're graphing necessarily. But we're going to bring the two together so you can take a look at the difference between x-intercepts and then solving. So if I ask you to solve x squared minus 4x plus 5 equals 0, use the quadratic formula to do that. So use the quadratic formula. You should already have that memorized. And then we're going to simplify that quadratic formula as well. So pause it, please, and do that. So that therefore gives me x equals 4 plus and minus. So 16 minus 20 is negative 4. This is the part that most people mess up, remember? So take care when you're doing that part. And that's going to give you that imaginary piece as well. So now I have the square root of negative 4. So thinking back to the previous problem, otherwise just write it out. That's the same thing as the square root of negative 1 times 4, which is I squared times 4, square root of that, which is 2I. So therefore, x equals 4 plus and minus 2I all over 2. So we're simplifying our radical down. And lastly, we have to simplify that. You can either think about factoring a 2 out of the top or dividing each of these parts by 2. Therefore, x equals 2 plus and minus I. Please be careful when you simplify that. Either factor the 2 out of the top and then simplify the formal 1, or remember both of these pieces are being divided by 2. Those are the two solutions to this quadratic equation. Those two solutions. One of them is 2 plus I. The other is 2 minus I. Both of those are called complex solutions. And then part C says a real number plus or minus a multiple of I, like each of the solutions to this, so right here, are called complex numbers because there's a real part and an imaginary part to it. So real number part, imaginary part. So those are complex numbers. Check one of the solutions from part B by substituting into the equation for x and simplifying your results. So what I should be able to do is take either one of these and substitute them in for x. So 2 plus I squared minus 4 times 2 plus I plus 5 equals 0. So I'm going to go through and simplify this. So this is 2 plus I times 2 plus I, which is 4 plus 4I plus I squared. I'm subtracting this whole amount, so minus 8 minus 4I plus 5 equals 0. I to an exponent has to be simplified. So this is 4 plus 4I minus 1 minus 8 minus 4I plus 5. I definitely could have combined like terms here. And then I combine all my i's. 4i and negative 4i, that's 0. And then I have a 4 and a 5, which is 9, and that's a negative 9, so that's 0. So it's a true statement, so it checks. It's showing that, yes, I did solve it correctly. So just a quick check showing how you can check complex numbers and even just working with complex numbers. We treat I as if it's a variable. It does have an algebraic number, but we do treat it like it is a variable. Okay, so in this problem, what you're going to go through is you're going to sketch each of these graphs, and then we're going to look at the types of roots that you're going to get, and then we're going to generalize that and kind of put it together. So in this first one, we have a quadratic that shifts 3 units left and 4 up. So 3 left, 4 up. And our A value is positive, and it's 1, 1, 2, 4, etc. So that's the typical opening. So we have that. So we sketch that. Are there any roots? Nope. Okay, now we're going to sketch this one. This one is going to shift 3 units to the left and have our traditional opening 1 over 1 up, 2 over 4 up, etc. Does that have any roots? Yep. Oh, I made a mistake on the first one. I went up instead of down. Haha. Sorry about that. 3, negative 4. You were probably all yelling at me from home, weren't you? So does that one have any roots? Yes. Yes. And then we have this one. And this one is what I was trying to do before. 3 left, 4 up. Does that one have any roots? No. Well, yes. Well, what's a root? Remember, a root is the value of x when y is 0. So, in this first one, we can see the 2 roots. The 2 roots here are at x equals negative 1 and at x equals negative 5, if I drew it well. Here, we have a double root at x equals negative 3, a double root. So notice there are 2 roots here, there is a double root here, and then what about here? If I were to try to find the roots by solving this, am I going to get solutions? Yes, I am. Are there any x-intercepts? No. So there are no x-intercepts. And there are 2 roots. And the reason I know that, I can solve it. So I have x plus 3 squared plus 4 equals 0. So subtract the 4. Square root, positive and negative, square root of negative 4, which means it's x plus 3 is positive and negative 2i. So x, therefore, is negative 3 plus and minus 2i. There's 2 solutions there. So, yes, there are 2 roots. 2 roots. Double root, 2 roots. 2 x-intercepts, 1 x-intercept, no x-intercepts. So now, I'd like to make some general statements about the relationship between the graphs of parabolas and the kind of roots their equations have. So therefore, if it crosses the x-axis, it crosses through the x-axis, then we have 2 real roots. If the vertex is on the x-axis, there is 1 double real root. If it does not cross the x-axis, there are two complex roots because there will be an I in it. So, lots of stuff we did today. We learned how to find an imaginary number. We learned how to solve a quadratic when we had to use the quadratic formula and simplify with that imaginary. And then we also learned how to figure out, based upon the x-intercepts, how many real versus complex roots we have.